So hi guys, welcome. Today we will be talking about what is AdaBoost and what are its advantages. How can we use AdaBoost to real world applications, right? So what is AdaBoost? So AdaBoost basically stands for adaptive boosting, as you can see. So what is adaptive specifically? Adaptive as in it will adapt, right? Adapt to what? So basically the idea is you have some data set here. This data set is child. This is child who is starting to learn everything. Okay, who is starting to learn, right? Now what is adaptive? Adaptive means whatever child sees, the surroundings, conditions, the type of friends, okay, the type of education, right? So all these things he will adapt to the circumstances, right? He will start learning how the surrounding is teaching, right? So in the similar sense, we have already undergone a detailed video on boosting. What is boosting? So similar idea is for adaptive boosting, right? So what is adaptive boosting? There are certain data set, right? And we have different subsets. Okay, we have different subsets of data set, and on every data set there will be a model, there will be a training, right? There will be a model. Okay, so similar is so we will be looking detail of this. Before that, I'll just introduce you who has invented it, right? So it was introduced in 1997 by Freund and Schapire. Okay, Freund and Schapire. So basically it deals with classification problems. So you must be aware what is classification. Classification is basically you have to classify the given data. Okay, so classify into what? Let's say if we talk about mail, then we need to classify it as spam or ham, right? If you talk about a person is diabetic, okay, so what you have to classify? Whether the person is diabetic or not, right? So this is basically this particular kind of classification is binary classification, right? So we are specifically here dealing with binary classification, right? Binary classification. So this is the data set. You have different basic data. So how AdaBoost starts? It starts with uniform distribution of weights. So these are basically the weights which are given equally to all the data points, right? Or you can say all the models. Okay, so equal weight to all observation, right? So first one will be equal weight to all observations, right? Now we will start with single weak learner. So this is model 1 and we call it as weak learner. Okay, so this model will classify points, or you can say observation, to yes or no. So it can be true, false, it can be yes, no, it can be diabetic or non-diabetic, it can be anything which has binary classification. Okay, right? So this will be the model which we are getting after this process. Okay, and this model we call as weak classifier 1. Why we are calling it as weak classifier 1? Because there are some misclassified points. Misclassified as in this is the decision boundary. Okay, this is decision boundary, and this red one is the misclassified data point which is on the yellow side of the data set, right? So this is the misclassified point. Okay, this is the weak learner one. Now similarly, what is the next step? These are the initial predictions. Okay, and this is the pattern which is not captured by the weak learner, right? So this we call as misclassified point. So this is the pattern which is not captured by weak learner, right? So what is the next step? So this point will be taken care by next weak learner. Okay, so the patterns which are not captured by previous weak learner will be captured by the next weak learner. So how this pattern will be captured? It will assign more weight to this misclassified point, right? It will assign more weight to this misclassified point. And what is the idea? If there is more error in the weak learner, lesser is the weight given to it. So this is now weak classifier 2. Okay, So there are many such data points, right? Now what we are doing is we are taking weighted sum of all the weak learners. So this is how it will be done, right? So this will be the final predicted model. Okay, so these steps will iterate continuously, okay, to create a specified number of weak learners. So this we will specify in the model, okay, how many weak learners we want, right? And the weighted sum of all these weak learners will ultimately fetch us the final predicted model, right? So this is the idea. So let me tell you what is the concept behind updation of weight, how the weights are updated. Okay, so basically we are starting with base model with equal weights given to every observation, right? In the next step, observation which are incorrectly classified will be given higher weightage, right? So that a new weak learner is trained. Is it? Yes. It will give more attention to these misclassified observation. This is what we learnt above, right? So in the end, we are getting a series of models that have different say. Okay, so basically we are getting different models. This is weak classifier 1, okay, this is weak classifier 2, and so on. So these are different models, and each model will have a error rate, right? Each model will have something called as error rate, and the error rate, the models whose error rate are lower will be given more importance, right? More importance, right? It's very basic logic, right? Somebody who is committing less mistake will ultimately be given more importance, right? Okay, so this is the error rate, and if error rate is lesser, then the model will be given more importance. It means that the say of the model will be more, means alpha of the model is more. So what is alpha? Alpha we define as 0.5 ln, so that's natural log 1 minus total error divided by total error. So this is how we define the amount of say or alpha in the model. Okay, and the limit of the error is, it will be from 0 to 1. Okay, and what is error? Error is equal to number of misclassified observation divided by total observation. So let's say in this case, you can see here we have 1 2 3 4 5 6 7 8 data points, and we have 2 data points which are red, and those are misclassified, right? So 2 divided by 8, right? Number of misclassified observation divided by total observation, right? So 2 divided by 8, it will be 1 by 4. What will be the amount of say? Amount of say will be 0.5 ln 1 minus 1 by 4. So total error is 1 by 4. Okay, so 1 minus 1 by 4 divided by 1 by 4. Okay, so whatever the value is coming, that will be the amount of say for a particular model, right? I'm talking about a particular model. Okay, so weak learner, I have already told you, it is at least better than a random guesser, right? So let's say tossing of coin. So if you guess randomly, you will have the error rate more than or equal to 5.5, right? So what will be the error rate for weak learner? It will be lesser than 0.5. So that is called as weak learner. Okay, how do we define weak learner? A weak learner is a model which performs at least better than a random guesser model. Okay, so this is how we define weak learner. Okay, now why we are taking weak learner only? Why we are taking weak learner? Because so through weak learners we can ensure the variance of final model will be lesser, like you can control the variance, right? And what is the second advantage of using weak learner? We can train the ensemble very quickly, right? So through weak learner we can easily train the ensemble, right? So it will lead to faster computation time. These are the basic advantages of weak learner. Using weak learners we can achieve the efficiency of the model. So we have already found out the amount of say, that is alpha. Okay, and the idea behind the updation of weight in AdaBoost model is like this. So for correct predictions, new sample weight becomes old weight into e to the power minus alpha. So for correct prediction, we don't give importance, right? We don't give weight to the observation, right? That is why we are considering negative sign with alpha. And for incorrect prediction, the sample weight will be old weight into e to the power alpha. So this will make the weight more for misclassified points, right? So basically what we are doing is for misclassified points here, you can see this was our misclassified point and we increased the weight, right? As you can compare from the different observation, we have increased the weight of this misclassified point. How we are increasing the weight? We have amount of say, right? And we will perform old weight into e to the power alpha for misclassified point only, right? For incorrect predictions. Okay, so this is the idea. So when we do it, we also normalize the weight because the summation should come 1. So normalizing technique, you must be knowing the sample weights divided by sum of new sample weights, right? So when you add all the new sample weights divided by summation of new sample weights, it will come unity, right? So how is the graph? How is the graph of amount of say versus error rate? So when the base model perform with less error overall, right? Where is less error? This is the less error. Okay, this is the error rate. So we have less error. So when you have less error, you have more amount of say, right? You can see here it is approaching 3, like it is positive, right? So you can see in the plot above, alpha is the large positive value. You can see here it is alpha is the large positive value. Okay, if the error rate is 0.5, you can see somewhere in the middle. Okay, so if error rate is 0.5, it means that it is not sure of the decision, right? So you can see here alpha is 0, here alpha is 0. So this weak learner will have no say or significance in the final model. So it will have no say. So it cannot distinguish, or it cannot find out whether I'll go with head or I'll go with tail, right? Because it's a binary classification. Okay, so it cannot say whether it will be true or false. If the model produces large error, you can see here from here up to here you have large error. Okay, then alpha will also have large negative values. Okay, and here it will have very low say in the overall model. Okay, so this is the idea. So this is very important, amount of say versus error rate. Okay, this is the exponential graph. Now I'll just be giving you a numerical example how we create the resample data. Let's say for weak learner we want to create. So these are different models. Okay, so these are models and these are their alpha, or you can say amount of rate. Here the prediction is +1. It means that the person is diabetic. Okay, and here the person is non-diabetic, that is -1, and these are the different models. Okay, or you can say the different you have amount of say or alpha value. So what we will do, we will be performing sum. Okay, sum of product of alpha and the decision. Okay, so here 0.477 is the value of alpha and this is the decision. Okay, whether it is diabetic or non-diabetic. Okay, so alpha into the decision of that particular model. Okay, similarly we will be multiplying all these, and here non-diabetic means -1. So all the alpha will be multiplied by -1 and it will be added to each other and into the final model. So overall we are getting +1 plus 0.162. It means the person is diabetic. Okay, because the value is coming positive, right? So it will finally predict that a person is diabetic. So this is the maths behind the AdaBoost model. Okay, now let us go further. We will be creating AdaBoost classifier using Python. So how do we do that in Python? So step 1 will be importing necessary libraries. Okay, step 2 will be loading the dataset with some visualization, right? So we will be checking whether the dataset has null value or not, whether the dataset has extremely high or low values or not, right? So all these things we have to check using box plot and various other visualization techniques, right? Step 3 will be feature engineering. Under feature engineering we will have to perform certain categorical and numerical engineering we have to do. So there are certain data set which are having some categorical data. Okay, so what we have to do, we have to go for encoding. Okay, so machine learning understands zeros and ones, right? So we have to convert all these into numbers. Okay, we have to convert these into numbers, and for numerical we have to scale the data set. Okay, after doing scaling with numerical and numerical dataset and encoding with categorical dataset, we will concatenate the features, right? After concatenating, we will be extracting the target, okay, and we will be mapping to yes and no. Like let's say the person is diabetic, we will put it as yes or 1, okay, and if the person is non-diabetic, it will be mapped as 0, okay. So this is how we will be doing. After doing this, we will perform train test split, and after that model fitting. So for model fitting, we have certain parameters. The first one is base estimator, okay. The second one is number of trees or models we have to make, and the third one is learning rate, okay. For classification, we have to find out the accuracy score and confusion matrix. And for regression tasks, which we are not doing right now, we have to go for R2 and RMSE, right? So this we presently we don't have to do. We just have to concentrate more on accuracy score and confusion matrix, right? So this is how we will be doing, okay. We will be performing the model, the classifier using Python, okay. So let's do it.